Welcome to your lecture on Chapter 2, Basic Chemistry. Chapter 2 begins chemical elements today. We'll talk about an atom, an isotope. We'll learn the difference in a molecule and a compound. During this discussion, we'll also learn the basics of a periodic table. We'll talk today about chemical bonding, particularly ionic and covalent, and a special type of chemical bonding called hydrogen bonding. We'll look at the properties of water as well as acids and bases. We'll talk about the common measurement tool for acids and bases, and we'll look at some common household examples of acids and bases. To begin on page 20 with chemical elements. When you're discussing chemical elements, you're talking first about matter, anything that has mass and takes up space. Matter comes in three main forms. We have solid, we have liquid, and we have gas. Now there's a fourth state of matter, plasma, which we're not going to discuss today. There are 92 elements that make up matter that we consider naturally occurring, those that we have not chemically created in a laboratory situation, but you can go out, dig up a piece of the earth, and find these 92 naturally occurring elements. To be an element means something cannot be broken down into any substance that has different properties. When you break it into its smallest piece, it is matter. Only 6 of these 92 naturally occurring elements make up 98% of any organism. We refer to those 6 with the acronym CHNOPS, whereas C stands for carbon, H for hydrogen, N for nitrogen, O for oxygen, P for phosphorus, and S for sulfur. The atomic structure is the basic structure of any element is going to be composed of 3 what we call subatomic particles, whereas sub refers to below, so we mean below an atom or smaller than an atom. 3 components to an atom. We have a proton, which is positively charged, located in the nucleus of an atom. We have a neutron, which has a neutral or no charge, also found in the nucleus of an atom. And then orbiting around this nucleus, we have negatively charged electrons. Now, most of an atom is actually empty space. There is a tightly packed nucleus of protons and neutrons, randomly orbiting electrons on the outside, but mostly empty space. Every element of these 92 naturally occurring elements is represented by a unique atomic symbol. Now, most of these are going to look unusual as far as sodium being Na, or iron being Fe. That is because this portion of the name comes from their Latin term as ferrous for iron. So some symbols you'll see referring to their Latin, some symbols you'll see referring to their English term, whereas C for carbon. Let's turn to your periodic table on page 954 and look at a few of the atomic symbols. You'll see the B, below the B it stands for boron, H for hydrogen, He for helium, all after their common English terms. But if you look down that very first row, you'll see on the 4th one down a K, K for potassium, again after its Latin terminology. You'll see as you progress from the left to the right that sometimes there's a single letter, sometimes there are 2 letters. In the case of the 2-lettered names, the first one is always capitalized. Now look at the numbers, because the numbers each reference something. In one case, you may see the numbers arranged in this way, where we have what we call a superscript, meaning it is above, or a subscript, where it is below. In your textbook, these exact same numbers are represented this way, where technically they're both superscript. Well, an easier way to learn this is by size. The larger of the numbers is always referred to as your mass number, sometimes referred to as the atomic mass. The smaller of the 2 numbers is your atomic number. Now the mass number is most often found in a decimal form. Your textbook, for ease, has rounded that number for you. You may find it to be 22.989. That would round to 23. We may find something 10.023. That would round down to 10. Your textbook has taken care of the rounding for you and has already done that. Talk about what the numbers mean then. We'll start with the atomic mass or the mass number. That is the count of how many protons plus neutrons are contained in this atom. For carbon, there are a total of 12 protons plus neutrons in the nucleus. The atomic number refers to the number of protons only in the nucleus. Using this, we can easily and mathematically figure out the number of neutrons. If mass number is protons plus neutrons, and atomic number is only protons, then math will simply tell me the difference. Protons plus neutrons, this is protons only. Therefore, in this example, I have 6 neutrons. Let's look at your periodic table and work a few examples of this. Let's start out with lithium. Li, lithium. If you'll look on your periodic table, it is in the far left-hand side, is in the second down, where you'll see a number 3, which is your atomic number, and a number 7, which is your mass number. This tells me the number of protons, whereas this tells me the number of protons plus the number of neutrons. So for lithium, simple math would tell me that I have 4 neutrons and 3 protons. Now there are 3 components to any atom. We have protons, we have neutrons, and we have electrons. There is a simple way to tell the number of electrons. In an atom, if protons are positive and neutrons are neutral, electrons are negative. In order to keep an atom electrically neutral, then the number of positive protons must equal the number of negative electrons. Otherwise, we would have a charged atom. So to keep an atom electrically neutral, the number of protons will equal the number of electrons. So in the case of carbon, where I have 6 protons, then I would also have 6 electrons. So let's return to lithium. Atomic number 3, atomic mass 7, and I want to know the number of protons, the number of neutrons, and the number of electrons. Our protons would be 3, our neutrons would be 4, and to keep this atom electrically neutral, our electrons must equal our protons. Let's work a few examples. Looking at your periodic table, if you'll go to the right and find the symbol B for boron, find the atomic number, find the mass number, and then calculate for me the number of protons, the number of neutrons, and the number of electrons. And I will pause for a few moments and allow you to do those calculations. You could easily begin by saying there are 5 protons. Electrons must equal that for it to be neutral. Then my math would come into play. 11 minus 5 would be 6. So I have 6 neutrons. Let's try another. Let's return back to the left-hand column of your periodic table and find sodium, Na. Atomic number is 11. Atomic mass or mass number is 23. The number of protons, the number of neutrons, and the number of electrons. Number of protons would be 11, electrons 11. The number of neutrons would be 12. You need to practice doing these on the periodic table. This numbers will be relevant a little bit later in lecture. They'll also be relevant on your quizzes. So please practice calculating the number of protons, the number of neutrons, and the number of electrons for any atom found on the periodic table. So let's talk a little bit more about the periodic table. You're seeing a small portion of the periodic table on my screen. If you're referring to page 954, then you're seeing the expanded periodic table. The periodic table is organized in two ways. One, we have vertical columns that are called groups, or they're also called a family, or families. Then we have our horizontal rows, or our periods. Now, there are 18 families or groups on the periodic table and 7 periods. This is period 1. It's a horizontal row. This is period 2, this horizontal row. This is period 3, horizontal row. This is family or group 1, family 2, family 3, and so on. We can use this way to locate something on the periodic table that we may not be familiar with. You would locate the correct period and follow it to the right, and the correct family and follow it down. Let me give you an example. Back to sodium. We would say that sodium belonged to period 3, family 1. It's much like using a map where you would find location J11. Put your finger on J, put the opposite finger on 11, guide until the two meet, and where they meet is your coordinate. Same is true for the periodic table. Sulfur. We would say sulfur was in period 3, family or group 6. So now refer to your periodic table on page 954 and locate for me the element that is in family 11, period 5. I'll give you just a moment. Count down and find period 5, and then count over and find family 11. That should land your fingers on the symbol Ag, which is the Latin term for silver. This is a quick method to find anything on the periodic table by simply putting one finger on the family, one finger on the period, guide until the two meet. Let's do one more. Let's look for family 16, period 2. Family 16 or group, period 2. What element is located in that position? Should have located oxygen. Now on your periodic table, you'll see that is in family 16. On this reduced table here, you'll see that there is a gap missing here of families 3, 4, 5, all the way until you get to family 12. Think about a family. Families are comprised of several different. You can have your mother, your father, your brother, your sister, and you. Your family could be your grandparents and other siblings and you. It could be an adopted sibling, but think about what a family really is. A family is someone who has, or a group that has something in common. You live under the same roof. You share the same guardians. You share the same parents. You live in the same area. You share the same blood. The key about a family is sharing something common. Families on the periodic table share common characteristics. Everyone in family 1 shares common characteristics. The same is true when you get all the way over here to what is technically family 18 if you're referring to your periodic table. So we are grouped together based on characteristics. noting that everyone in a family shares some common characteristics. Let's talk about electrons a little more. In an atom, we have positively charged protons, neutral neutrons, both found within the nucleus, and orbiting around that we have negatively charged electrons. Now, positive and negative, opposite charges, we know that opposites attract. Those negatively charged electrons are attracted to those positively charged protons. And as long as those numbers are balanced, we have what's called a neutral atom. Electrons orbit around the nucleus in things that we refer to as an orbital. Now, the key is this. An orbital is where we think they're most likely to be found. But in actuality, at any one moment, we can't really determine where an electron is. We can, however, assume that they are going to be somewhere hovering around the nucleus because of that positive and negative charge attraction. We also know that with the use of energy, you can push an electron out of one orbital into another orbital. And as they move from one orbital to another, they release energy. We refer to these different orbital levels, these different energy levels, as electron shells. We can depict these using something called a Bohr model, named after Niels Bohr. If you'll look on the bottom of page 23 in your text, you'll see some examples of common Bohr models. Bohr models use this electron shell theory, which is a concentric circle around the nucleus, and there is a set rule for how many can go in each. It's referred to as the octet rule. Octet refers to the number 8. Here are the basic rules. We have a nucleus, and inside of our nucleus we have protons and we have neutrons. So we'll say this is our nucleus. Orbiting around the nucleus in nice round circles, we should find our electrons. We refer to each of these as an electron shell. Now, every electron shell has a certain number of spots on it, or let's think about them as seats. Let's use a rowboat, for example. On a rowboat, in the very front, there may only be one seat. The next row, there may be 2. The next row, 3. As you get to the middle of the rowboat, there may be as many as 4 seats. And then as you progress towards the tip of the rowboat, you may return to only 1 seat. By placing people in these appropriate seats, we keep the rowboat balanced, make it easy to move across the water. An atom is no different. There are a certain number of seats on every electron shell. We would like these seats to be filled or balanced before we progress on to another row. In an electron, the innermost shell only has 2 seats, let's say. Only 2 places in which electrons may occupy. Every row past that has at least 8 seats. Or a multiple of that, 16, 24, 32. To keep a balanced boat, we would like to see at least the minimum number met, 8. It's what we refer to as the octet rule. Atoms with fewer than 8, other than in that first level that only holds 2, we consider those atoms reactive. They're continually seeking another atom to help fill up their seats. If you have 3 or less electrons present, meaning you have 5 open seats, that atom has a tendency to donate its electrons and give them away to another atom in order to balance it. If there are 5 or more filled sections or seats, then that atom has a tendency to gain electrons in order to make it stable. 4 on the middle, it's a special situation we'll look at in a moment. Let's go back to lithium again. Lithium has an atomic number of 3, an atomic mass of 7. I can calculate from that the number of protons, the number of neutrons, and the number of electrons. 3 protons, 3 electrons, 4 neutrons. If I want to take these numbers and now convert them to a Bohr model to represent whether this atom is stable or not, it's easily done. In the nucleus, there are 3 protons. There are 4 neutrons. Then I have my electron shells. On the first shell, I can hold no more than 2 of these 3 electrons. So if I put 2 electrons on the first shell, that leaves me 1 electron. That first shell is full. It will not hold any other electrons. So there would be another electron level in which I could place my 3rd electron. Now, you have to ask yourself, is this atom chemically stable or is it chemically reactive? Well, to be stable, we need 8 or a multiple of 8 on that outer level. Well, there's only 1. This atom is chemically reactive. It is in this 3 or less category. So this atom is constantly seeking another atom to join with so that it may donate its 1 electron. Because when it donates its 1 electron and loses this electron shell, then it is stable, because the first one is stable with only 2. Let's work a few examples so that we can get comfortable with Bohr models. Let's look at how hydrogen was done. If I go to the periodic table and find hydrogen, I'll see that we have an atomic number of 1, an atomic mass of 1. This is actually a decimal. There would be 1 proton in the nucleus and only 1 electron. Is this atom chemically stable? No. It is seeking another partner in which to bond with to achieve stability. Let's look at sodium. So I need to be able to find sodium on my periodic table. So here's where I'm going to use my family and my periods reference. Remember that families are your vertical columns, periods are your horizontal rows. Sodium is in family 1, period 3. That would give me an atomic number of 11, an atomic mass of 23. I would have 11 protons, 12 neutrons, 11 electrons. Taking this data, I should be able to draw a Bohr model of sodium. 11 protons in the nucleus, 12 neutrons in the nucleus, 11 total electrons. Let's make a little tally over here. The first electron shell or orbital only has 2 seats. So if I place those 2 electrons there, I now have 9 more electrons to disperse amongst this atom. Another orbital. The octet rule says that 2 on can have 8 or a multiple of 8. Now this atom is trying to achieve stability. It wants to fill as many rows as it can with at least minimal stability before it moves on to another one. So we could place 9 on the second level, but it would not be as stable as if we placed 8, because that fits the octet rule. And we allow 1 to go to this other orbital. Now this does make sodium highly reactive, but sodium can very easily find someone to give this 1 electron to. That is why sodium is one of the major components of many of our salt products. Very easily chemically combines with something else in order to lose this 1 electron and achieve stability. Let's work another one. Let's go just above sodium to beryllium. Chemical symbol for beryllium is Be. Atomic number 4, atomic mass 9. That would be 4 protons. Mathematically, I can figure out how many neutrons. 5 neutrons. 4 electrons. I would have 4 protons in the nucleus, 5 neutrons in the nucleus. My first energy level can hold no more than 2 electrons, and I am left with 2 electrons. This atom as well is not stable. It will seek someone to donate those 2 electrons to. Let's move over to family 17. Look at fluorine. Fluorine is in family 17, period 2. The atomic number for fluorine is 9. The atomic mass is 19. 9 protons, 10 neutrons, 9 electrons. 9 protons in the nucleus, 10 neutrons in the nucleus. First energy level would hold 2 of these 9 electrons. Second energy level can hold 8 or multiples of 8. I only have 7, so we will give it 7 out of electrons. Finished with my Bohr model. Now I can ask myself, is this atom chemically stable or is it chemically reactive? With 7 electrons on the outer level, it is reactive because we must have 8 or multiple of 8. However, this atom, instead of losing its electrons, would seek to gain 1 electron from another atom to make it chemically stable. One more. Let's progress just to the right of fluorine and do neon. Neon's atomic number is 10. Atomic mass is 20. That would be 10 protons. Going to be the same. 10 neutrons, 10 electrons. 10 protons in the nucleus, 10 neutrons in the nucleus. My first energy level can hold no more than 2 electrons. I'm left with 8. Neon is a chemically stable element as it exists in nature. Everyone in family 18, helium, neon, argon, krypton, xenon, radon, they're all naturally chemically stable. That is why we use neon for signs, why we use helium for balloons. So knowing what we know now about that, let's look back at hydrogen. Hydrogen only has 1 electron in its outer energy level, making it very unstable and very reactive. Knowing just that simple piece of chemistry should explain why the Hindenburg blew up, the big German airship that they filled with hydrogen. Hydrogen is very chemically reactive. It didn't take much to spark that and cause it to burn. Today's hot air balloons, today's balloons that you see, the Goodyear blimp, they're filled instead with helium, which is a part of family 18, which is naturally stable on its own. We call family 18 the noble gases. Think about nobility. Nobility is a very stable clique. They are self-sustaining. They don't marry outside of nobility. They don't socialize outside of nobility. They are very independent. All of your noble gases behave the same way. They're chemically stable on their own. They don't require other elements to achieve stability. They don't, therefore, mix with other elements. If we look back at our examples of Bohr models, then we'll see a few other examples. There is carbon, there is nitrogen, oxygen, phosphorus, sulfur. You can choose to actually draw the electrons out as they've done here, or simply write the number of electrons on the orbitals. So 2 electrons, 5 electrons. So what about carbon? Carbon is that in the middle example we're going to talk about shortly. Let's look at nitrogen. What does nitrogen need to become stable? It has 5 electrons. Octet rule says I must have at least 8 or a multiple of 8. So nitrogen would need to gain 3 electrons to be stable. Oxygen has 8 electrons on the outer level. Oh, excuse me, 6. Sorry, counted too quickly. With 6 electrons on the outer level, it is not stable. In order to be stable, it would need to gain 2 electrons. Phosphorus. Phosphorus has 1, 2, 3, 4, 5 on the outer energy level. It is in the same position as nitrogen. It needs to gain 3. Sulfur. 1, 2, 3, 4, 5, 6. It's in the same position as oxygen. To be stable, it would need to gain 2 electrons. You need to take a moment, look at the Bohr models, make sure you understand how the electron number was derived and how they are placed on the energy levels. Remember the basic octet rules. The first energy level can hold no more than 2. Every energy level thereafter should hold an 8 or a multiple of 8.